When the phrase quantum observer effect is heard, many people conjure up a mysterious and fascinating scenario in their minds: that human consciousness alone transforms reality, that the gaze virtually rewrites matter. However, the truth that physicists have long emphasized is far simpler, yet equally unsettling. In quantum physics, the observer is not a mind that perceives or thinks, but an interaction mechanism that measures and physically affects the system. In other words, what is decisive is not the presence of consciousness, but the inevitable contact that occurs during measurement. Werner Heisenberg's uncertainty principle and Niels Bohr's complementarity approach clearly demonstrate that absolute neutrality is impossible at the subatomic level. Because the moment you try to measure the position, velocity, or behavior of a particle, you inevitably transfer energy to it, alter its path, or disrupt its wave properties. Although this is not noticeable in everyday life, it becomes an unavoidable law in the microscopic world. To acquire information means to intervene simultaneously. A simple analogy suffices to explain this fact. When you want to see an object in a dark room, you turn on the light. However, this action is not just seeing the object. It means sending millions of photons to it. These photons hit the object, change direction, and reach your eye. In everyday life, this interaction is insignificant. But on a quantum scale, looking becomes an intervention as significant as directly touching. This is precisely the point that popular narratives often miss. Quantum physics does not claim that human consciousness creates reality. Rather, it clearly demonstrates that reality is not a fixed and unchanging structure entirely independent of measurement. This is where science's quiet but firm correction begins. Physics does not focus on consciousness. It focuses on the interaction and measurement process. As Niels Bohr particularly emphasized, it is impossible to separate what happens in the subatomic world from the way we observe it and the measuring tools we use. Because measurement is no longer a tool outside the observed system, but an integral part of it. Therefore, quantum mechanics does not completely reject objective reality. Rather, it treats it as a conditional, context-sensitive, and multifaceted structure. Reality manifests itself in different ways depending on the question you ask and how you ask it. That's why scientists use particularly cautious language on this subject. When misinterpreted, the observer effect can open the door to mystical expectations, illusions of control, and scientifically unfounded conclusions. But when understood correctly, it conveys a far deeper message. The universe is not a passive stage. It is a dynamic process that reshapes itself with every interaction. And perhaps the most striking fact is this: at the quantum level, there is no possibility of a completely independent, unbiased, and ineffective observer. Anyone who wants to make measurements inadvertently becomes part of the game. Science neither glorifies nor dramatizes this. It simply accepts it. Therefore, the observer effect is often perceived not as a misunderstanding, but rather as an incomplete and superficial concept. Chapter 2: The Double Slit. The story of a universe that is a wave when not observed. It all began in the early 1800s with a remarkably simple experiment conducted by Thomas Young in a dark room. An experiment that would silently shake humanity's understanding of reality. Wanting to understand the nature of light, Young placed a plate with two narrow slits in front of him, and then passed a single light source through the slits. The logic was simple. If light consisted only of particles, as Newton had claimed, then the light passing through the two slits should have created two bright lines on the screen behind it. But this did not happen. On the screen, an interference pattern appeared, created by overlapping waves. The light seemed to pass through everywhere simultaneously. This result was considered merely an optical anomaly at the time, until the 20th century. A century later, physicists decided to perform the same experiment. This time, not with light, but with electrons. And that's when the real shock began. Because, as everyone knows, electrons were matter, meaning they should be small, hard, point-like particles. But when the experiment was repeated, the same wave interference patterns reappeared on the screen. Even when sent individually, the electrons behaved as if they were communicating with each other, propagating like waves. At this point, the physicists could still cling to a comforting explanation. Perhaps electrons behave like waves when we don't look at them, and like particles when we do. To test this idea, measuring devices were placed in the experimental setups. The goal was simple: to see which slit the electron passed through. And then, everything changed. The moment the measuring device was activated, the interference pattern disappeared. The wave behavior vanished. The electrons now behaved like clear, distinct, classical particles. The same experiment was repeated many times by different scientists in different laboratories. The result was the same every time: a wave when not looked at, a particle when measured. The truly unsettling question here was, what was the electron before the measurement? This question kept Niels Bohr, Werner Heisenberg, and Erwin Schrödinger awake for months, even years, because the issue was no longer the result of the experiment, but the nature of reality. If something isn't in a specific position until it's observed, how can we say it's there? Heisenberg didn't shy away from this dilemma. Rather, he explored it in depth. When he formulated the uncertainty principle, he was essentially saying, the more clearly you know the position of a particle, the more uncertain you make its momentum. While this seems like a technical statement, it carries a much deeper meaning. Nature behaves as it is measured. Niels Bohr went even further, arguing that in the subatomic world, it's meaningless to define reality independently of measurement, because measurement is an integral part of what is observed. That is, what the electron is depends on what question you ask it. This idea infuriated Einstein. God doesn't play dice, he said. According to him, the universe must operate with hidden variables unknown to us. But years later, Bell's experiments quietly undermined Einstein's hopeful objection. Reality wasn't as local and precise as we thought. Here, the double-slit experiment ceased to be merely an experiment. It became a mirror. The universe is like a mirror that makes us question how it looks at us. Modern quantum optics experiments have taken this conclusion even further. They have shown that even a single photon, a single electron, exists as a cloud of probabilities until it is measured. This cloud is mathematically definable, but it cannot be said to be there in the classical sense. However, the moment a measurement is made, these probabilities collapse and a single result emerges. The critical point here was, and still is, measurement is not passive observation. It is active interaction. The measuring device physically interacts with the quantum system, exchanging energy, and this interaction necessarily changes the system's behavior. Therefore, Scientists deliberately avoid mentioning consciousness when explaining the observer effect, because the issue is not whether someone notices it, but the nature of the measurement. Asking a particle, "Which slit did you pass through?" is like touching it. And in the quantum world, touching is changing. But the most disturbing aspect of the story is this: the universe reveals a different face the moment we try to learn something from it. It's as if nature says, "I will appear to you as you wish to see me." That's why the double-slit experiment is still told, still repeated, still debated. Because this experiment doesn't just give us information about the behavior of electrons or photons. It whispers to us, reality is not a static scene. It is a process shaped by interaction. And perhaps the most disturbing truth is this: when we look at the universe, we can never escape being a part of it. To look is to participate. To measure is to change. And in the quantum world, there are no exceptions to this rule. Chapter 3: Heisenberg's Uncertainty. Principle: Information isn't free. Heisenberg's uncertainty principle is one of the most misunderstood yet highly influential concepts in quantum physics. While initially appearing as an innocent technical limitation, our measurement technology is inadequate. It actually reveals a far more unsettling truth about how nature works. The universe doesn't allow us to know everything at once and completely. The more precisely you determine a particle's position in space, the more blurred your knowledge of its motion, its momentum, becomes. And when you try to determine its momentum, its position becomes uncertain. This isn't a matter of choice, it's an unavoidable price to pay. When Werner Heisenberg formulated this principle, what he meant was this: no matter how advanced the measuring instruments, no matter how precise the technology used, this limit cannot be overcome. Because the problem is not in the device, but in the fabric of reality. To observe an electron, you need to send a photon to it. And the moment the photon hits the electron's speed or direction changes. Therefore, acquiring knowledge requires direct intervention. In the quantum world, there is no such thing as a harmless glance. This fundamentally shakes the idea of complete knowledge that classical physics is accustomed to. In Newton's universe, theoretically, if you knew the position and velocity of every particle, you could calculate the future. The universe would function like a giant clock. But the picture presented by Heisenberg is entirely different. At the subatomic level, the universe is not a deterministic machine, but a system operating with probabilities. The future is defined not by definite lines, but by probabilities. Therefore, this principle is often explained in a simplified way. Because the uncertainty principle is not only a physical rule, but also a blow to the human mind's desire for control and prediction. People like to assume that they can completely measure nature, account for all variables. But quantum physics says, information is not limitless, and every piece of information has a price. Another critical point here is that uncertainty does not mean chaos. The quantum world is not random. It is governed by extremely precise mathematical laws. However, these laws describe probability distributions, not singular outcomes. In other words, nature answers not the question of what will happen, but with what probability will it happen. This distinction is one of the greatest intellectual differences between classical and quantum thought. Heisenberg's principle also implies that the observer inevitably becomes part of the system. No matter how hard you try to distance yourself, you cannot touch what you are measuring without leaving a trace. Therefore, complete neutrality is an illusion in the quantum world. To gain knowledge is to participate in the game. This fact has shocked not only physicists, but also philosophers and thinkers. Because if complete knowledge is not possible even at the fundamental level of nature, how meaningful is the claim of absolute certainty? Quantum mechanics delivers a quiet but powerful message here. Uncertainty is not ignorance, but a natural part of existence. In conclusion, Heisenberg's uncertainty principle teaches us that the universe never fully reveals itself. Every answer overshadows another question. Knowledge is something acquired, but it is never free. And perhaps the deepest lesson is this: reality is shaped not by how much we try to control it, but by how much we allow it to reveal itself to us. Chapter 4: Decoherence, the silent decision of reality. It was well past midnight, and the laboratory was enveloped in an eerie silence. The echoing footsteps, the hissing of coffee machines, and the lively conversations of the day were gone. Only the faint hum of fluorescent lights and the deep vibration of vacuum pumps remained, as if the building were breathing, but in a low voice, as if it didn't want anyone to hear. In this silence, a young physicist staring at a screen pondered, if a particle can truly exist in more than one state at the same time, why do we never see it? This question was one of the most unsettling riddles of quantum physics, and for years it had been sought in the wrong place. People, especially those new to science, had always been told, something changes when it is observed. Some even went further, claiming that human consciousness ruled the universe. But this young physicist, like many scientists before him, was beginning to realize that the issue wasn't about consciousness, but about loneliness. A quantum particle that is completely isolated, that is, almost entirely cut off from its surroundings, can behave like a wave carrying multiple possibilities simultaneously. However, in the real world, nothing is truly alone. Even the smallest particle is constantly in contact with air molecules, heat vibrations, electromagnetic fields, and even the background noise of the surrounding space. This contact, imperceptibly but unstoppably, was breaking the quantum magic. In the 1970s and 80s, one of the physicists who first seriously addressed this issue wrote in his lab notebook, "The problem is not the observation, it is the environment," because experiments had repeatedly shown that even without measuring instruments, the superposition state of a quantum system disappeared when it interacted with a sufficiently large environment. The particle could not remain unstable. It would be forced into a single behavior. This process was called decoherence. This seemingly technical word actually described a very familiar reality. Just as a whispered word in a crowded room quickly dissipates into a meaningless hum, the delicate information of a quantum system dissipates and is irreversibly lost as it interacts with its environment. There was no dramatic collapse, only a silent, statistical, and inevitable disintegration. Scientists designed incredibly difficult experiments to prove this. They cooled atoms to temperatures near absolute zero, attempted to isolate individual photons in vacuum chambers, and measured how even the slightest environmental interaction altered the results. The outcome was always the same. As contact with the environment increased, the quantum behaviors vanished, revealing the clear and stable reality we call the classical world. This discovery radically changed our understanding of the observer effect. A particle no longer needed human gaze to make a decision. A conscious eye had no special power. The decision was made by air molecules, heat, light particles. In other words, by inevitable interactions with the rest of the universe. Reality was shaped not by perception, but by the ability to not be alone. At this point, the mystical tales told for years began to quietly crumble. Quantum mechanics hadn't lost its mystery, but it had shifted direction. The mystery was no longer in the power of the mind, but in the statistical structure of nature. Decoherence transformed the quantum world from a fairy tale into a measurable, testable, and repeatable physical process. And perhaps the most striking result was this. What we call reality was actually a frozen mass of quantum probabilities in constant interaction with the environment. The table, the wall, our bodies, and even the brain that carries our thoughts were products of decoherence, not quantum uncertainty. Reality wasn't created by consciousness. It was determined by the environment. That night, when the young physicist in the lab switched off the screen, he realized the universe wasn't waiting for us to look at it. It had already made its decisions, silently, without consulting anyone. And perhaps this was the most unsettling, yet also the most honest truth that quantum physics could offer. Chapter 5: The Consciousness Debate. Why science is cautious. Since quantum physics began to engage with popular culture, perhaps the most misunderstood topic has been the role of consciousness. Because concepts like uncertainty, probability, and observation naturally lead the human mind to ask, could my awareness be changing things? But science must proceed with cold, repeatable evidence, not emotional intuition. And to date, there is not a single piece of experimental data that shows consciousness directly collapses the quantum wave function. This doesn't mean consciousness is trivial. However, to say there is a special, privileged, and physically defined power of consciousness in the workings of quantum mechanics goes far beyond the current scientific framework. All definitive experiments to date have been able to explain the collapse of the wave function through purely physical processes such as measuring instruments, environmental interactions, and decoherence. In other words, the system changes when it interacts with something, not when a person becomes aware of it. At this point, some respected scientists, such as the frequently cited Roger Penrose, have theoretically discussed the possibility that consciousness might be related to quantum processes. Penrose's ideas, in particular, that consciousness cannot be explained by classical calculations and may be linked to areas not yet fully understood, such as quantum gravity, are extremely interesting from a philosophical and mathematical perspective. However, there is a critical distinction here. These ideas are not proven theories, but research hypotheses. Therefore, mainstream physics is cautious. Science considers the difference between maybe and has been vitally important. No matter how attractive, meaningful, or intuitive a claim may be, if it cannot be experimentally tested, measured, and replicated, it does not have the status of scientific fact. This does not mean the subject is rejected. It means it is temporarily suspended. In fact, this is why the scientific world seems silent on this issue. Science does not like to engage in polemics with unproven claims. Rather than loudly refuting them, it sets them aside until data is obtained. This silence can be perceived from the outside as a concealment of something. But in reality, this is science's most fundamental reflex. Don't claim what you can't measure. Another dimension of the problem is this. If consciousness were a specific factor that collapsed the wave function, it would require a physical definition. When does consciousness come into play? Is a human necessary? Is an animal sufficient? Can artificial intelligence be considered conscious? Is a sleeping person conscious? None of these questions have a physically measurable answer today. And this uncertainty makes the direct inclusion of consciousness in quantum mechanics scientifically problematic. Therefore, instead of placing consciousness at the center, modern physics places interaction, environment, and measurement processes at the center. This approach has transformed quantum mechanics from a mystical belief system into a functional and predictable science. The problem of consciousness is, for now, not in physics, but in philosophy, neuroscience, and cognitive science. In conclusion, science is not incomplete because it doesn't say consciousness creates the universe. On the contrary, it is honest. Because the power of science lies not in answering questions, but in remaining silent until evidence emerges. And quantum physics, even through this silence, clearly tells us this: the universe may be far deeper than we think, but the way to understand it is not through wonder, but through evidence. Chapter 6. Why doesn't anyone say it clearly? In the late 1930s, in a small, quiet, and seemingly ordinary room in Copenhagen, a few physicists gathered around a table. The faint sunlight filtering through the window fell on the blackboard on the wall, chalk dust lingering in the air, and there was an awkward tension in the room, for the subject of discussion was not just atoms or experimental setups, but reality itself. Niels Bohr, with his usual composure, carefully chose his words, as if worried that each sentence could be misinterpreted. For there was a truth that everyone found intuitively unsettling. The universe might not be as there and static as we think. This unease became more pronounced as the results of the double-slit experiment were repeated over and over again. Electrons behaved like waves when unobserved, but when the measuring device was activated, they seemed to have decided to follow a single path. The experiments yielded the same result. The mathematics was consistent. The calculations matched perfectly. Yet the result challenged classical reasoning. Because this table silently but ruthlessly shattered the idea that reality is independent of measurement, constant, and absolute. This is precisely where the question arises as to why scientists don't speak openly. Because explaining these results loudly and in a simplified way leads to extremely wrong but appealing conclusions, such as reality doesn't exist until it's observed, or the universe changes when a person looks at it. Bohr and Heisenberg were aware of this danger. Heisenberg never forgot the reactions he received when he first proposed the uncertainty principle. People thought his words stemmed from the inadequacy of measurement tools, while the problem lay in the nature of things. One evening, walking with a young colleague, Heisenberg said, "The problem isn't in the equations. The problem is that people want the universe to be independent of them and completely observable. Because the classical worldview positions humanity outside the universe. Observations, measurements, and records capture what happens without distortion. But quantum mechanics has eliminated this comfortable position. Anyone who wants to make measurements inevitably becomes part of this process. This situation led not only to scientific unease, but also to profound philosophical unease. If reality is not independent of measurement, where does the boundary begin between what is and what we see? While scientists grappled with these questions, they were also aware that these issues could easily be exploited if they fell into the wrong hands. Claims like change the universe with your mind, create matter with your gaze, were fueled by hope rather than experiment. Therefore, science chose to retreat. Instead of speaking plainly, it spoke technically. It used mathematics instead of popular discourse, because mathematics is incomprehensible. However, words, especially reality, observation, and effect, are very flexible. Scientists preferred the issue to mature slowly among experts rather than the public drawing erroneous conclusions. Years later, when the theory of decoherence emerged, another reason for this silence became clearer. The decision-making process of quantum systems could be explained not by the existence of a conscious I, but by millions of tiny interactions with the environment. In other words, the universe wasn't waiting for a human to notice. Air molecules, photons, heat, and vibrations alone were enough to break the superposition. This finding pulled quantum mechanics out of a mysterious fog and placed it back at the foundations of physics. However, even this explanation didn't completely eliminate the unsettling truth. The fact that reality doesn't tell a single story, regardless of measurement, still held true. What question you ask, how you measure it, and what you interact with determines the answer you get. This was a silent blow to the fundamental assumption of classical scientific understanding. Another reason scientists didn't speak openly was responsibility. Because every powerful idea carries the risk of misuse. Just as the knowledge that the atom could be divided was handled with great caution, this knowledge about the nature of reality required the same sensitivity. Science wants people to develop understanding slowly but steadily, rather than becoming frustrated. In conclusion, nobody was hiding anything. It was known that every truth, when taken out of context, can be dangerous. The quantum observer effect isn't saying the universe is playing tricks on us. It's clearly showing that the universe doesn't have to conform to our classical intuitions. And perhaps the most unsettling point is this: reality may not be as certain as we think. But this uncertainty stems not from ignorance, but from the depths of the universe. Scientists prefer not to say this explicitly because being misunderstood is sometimes more dangerous than not being understood at all. And in quantum physics, there are certain truths that require patient silence rather than loud pronouncements to be understood. Chapter 7. The True Deep. Truth. Reality emerges through interaction. The real and often overlooked truth behind the quantum observer effect is this: the universe is not a frozen, static, and unchanging scene outside of us. Rather, it is a living and dynamic process shaped by constant interactions. At the subatomic level, nothing stands alone as a definite entity independent of context. Every particle, every field, and every possibility only becomes visible and meaningful when interacting with something else. This is the most striking, yet also the most honest, message of the quantum world. Here, it is necessary to correct an important misunderstanding. This truth does not place humanity at the center of the universe and does not support the claim that the universe is formed by human observation. What quantum physics says is far more neutral. It is interaction, not consciousness, that determines reality. A measuring device, a photon, a molecule of air, or even environmental noise can act as an observer for the quantum system. In other words, the universe does not wait for human consciousness. It is in constant interaction with everything. At this point, the concept of decoherence becomes critically important. A particle in isolation can simultaneously carry many possibilities. However, the moment it interacts with its environment, most of these possibilities are suppressed, and the system moves toward what we call classical behavior. While this process may seem like a moment of decision, it is actually the natural result of millions of tiny physical interactions. Reality takes shape step by step, silently, and without consulting anyone. This perspective points to a truth we don't notice in daily life, but constantly experience. For example, a musical note is only potential until it is played. There is no such thing as sound without the vibration of the air and its interaction with the eardrum. Similarly, a color or light does not gain meaning until it strikes a surface and interacts with the eye. The quantum world reveals this intuitive truth at the most fundamental level. Potential transforms into reality through interaction. This understanding also explains why the universe is so rich and unpredictable. If reality were static from beginning to end, change would only be superficial. But in an interactive universe, even small contacts can have significant consequences. Changing a measurement system, adding an environmental condition, or blocking an interaction can completely alter the resulting outcome. This isn't chaos. It's a deep and delicate balance. For scientists, this result is both fascinating and a cautionary tale, because this reality challenges the human mind, accustomed to the pursuit of certainty. We love results. We dislike uncertainty. But quantum physics presents uncertainty not as a flaw, but as a natural feature of the universe. And this uncertainty stems not from ignorance, but from the richness of interactions. Consequently, the true legacy of the quantum observer effect is this: the universe is not a passive object, but a constantly reacting process. Reality is not a static picture. It's like a sketch, redrawn with every contact. We are not at the center of this process, but neither are we entirely outside of it. With every measurement, every interaction, we share a line of the same story with the universe. And perhaps the deepest truth lies precisely here. The universe doesn't shape itself to fit us. Rather, we experience it to the extent that we interact with it. Reality doesn't wait silently. It responds when touched. Final thought: the story of a silent truth. As midnight approached, the young physicist, alone in the lab, gazed at the experimental setup on the table. The numbers, graphs, and wavy lines scrolling across the screen, seemingly meaningless at first glance, were silent witnesses to a story that fundamentally shook humanity's understanding of reality. This story had never been kept secret, never hidden. But to avoid misunderstanding, it had to be told within the narrowest, most technical limits of word. For the quantum observer effect was such a delicate subject that a misstatement could plunge science into darkness instead of illuminating it. This young physicist was not alone. Behind him was a chain of silence that lasted almost a century. When Werner Heisenberg, in the 1920s, while trying to understand the inner workings of atoms, realized that what he was measuring changed in the measurement process, he knew it was a scientific revolution. But he also felt how dangerously open it was to misinterpretation. Niels Bohr pondered the same question repeatedly during his long walks in Copenhagen. If the state of a particle is uncertain before measurement, are we discovering reality or merely describing it? It was a philosophical question, but the answer had to come only from experiments. Years later, physicists repeatedly setting up the double-slit experiment sometimes fell asleep in the control room on test nights, and sometimes couldn't believe their eyes when they saw the results. The electrons behaved as if they knew they weren't being observed. The entire order changed the moment the measuring device was activated. But at this point, the scientists were very clear. The electrons were unaware of consciousness. The universe didn't care about human consciousness. What was happening was much simpler, but much deeper. The measurement was physically touching the fate of the system. Therefore, science never said, "Looking creates reality." Rather, it repeatedly stated, "Measuring is interaction." When you send a photon, you don't innocently question it. You collide with it. This collision is inevitable on the subatomic scale. This fact has been proven, repeated, and confirmed countless times in laboratories. From the Casimir effect to quantum optics, from decoherence experiments to superconducting systems, everything points to the same thing. The universe is not passive. But precisely for this reason, this subject has never been explained to the general public in loud and ornate language. Because scientists knew all too well a danger they had seen many times in history. When interpretation replaces evidence, when belief replaces measurement, and when mystical power replaces interaction, science falls silent. Some, like Roger Penrose, question the role of consciousness. Yes, these questions were asked and are still being asked. But science did not present unanswered questions as if they had answers. It preferred silence to speaking falsely. The young physicist was actually aware of this as he turned off the screen in the lab. His work wasn't about making the universe magical. It was about showing that the universe is already astonishing enough. The quantum observer effect wasn't a secret. It was a carefully guarded fact. Because this fact displaced the idea of certainty that humanity was accustomed to, instead of placing humanity at the center. And this was often more unsettling than magic. Herein lay the truly striking point. The universe was built not on rigid rules and absolute results, but on relationships and interactions. A single particle was not a thing in itself. It gained meaning within context. There was no result without measurement, no clarity without interaction. This was not a weakness. Rather, it was an indication of incredible harmony. The universe was a constantly reacting structure, never locked into a single answer. And perhaps the final sentence that scientists have been whispering for years was this: the quantum observer effect doesn't make man God, but it makes the universe far more alive than we imagined. Reality is not just a background. It is a process that reemerges with every contact, every measurement, every interaction. Science does not exaggerate, embellish, or sanctify it. In short, it states, the universe speaks more through relationships than through certainty. And for those who grasp this silent truth, the world no longer seems the same. Because you realize that looking and measuring, seeing and touching, knowing and changing are never entirely separate things. And that is precisely where science falls silent. Because the experiments have already said everything they need to say.